Welcome to UBG Bytes, where we break down the latest in tech and security into bite-sized chunks. Today, we're taking on reinforcement learning RL. We've looked into how it's really powering AI, especially the large language models we see everywhere now.
Right. And also digging into what's actually happening under the hood.
Exactly. And critically, why understanding this whole learning process is essential for you as a security pro.
Absolutely. We've synthesized insights from, well, foundational papers, reports on autonomous systems, network defense applications, the whole gamut.
The goal being to give you the practical takeaways, right?
But
Cut through the hype.
precisely what you actually need to know.
All right, let's start at square one then. At its core, what? What is reinforcement learning?
Think of it like teaching through consequences. You have an agent, maybe a piece of software, learning to make decisions just by doing things in some environment.
Okay, not like supervised learning where you give it all the answers.
Exactly. No labeled input-output pairs here. Instead, it acts, and then it gets feedback. A reward, maybe, or a penalty, based on the outcome.
So it's basically trial and error, trying stuff and seeing what sticks.
Kind of, yeah. But it's directed trial and error. It uses that feedback to figure out the best sequence of actions over time to get the maximum possible cumulative reward.
Can maximize its score, essentially.
You got it. And, to keep the main pieces straight, there's a helpful acronym, EZAR.
EZAR. Okay, what's that stand for?
It's the agent, the learner, or decision maker, the environment it interacts with, the state, which is what the agent currently observes, the actions it can take, and the reward signal it gets back.
Agent, environment, state, actions, reward. ESAR. Got it.
And the whole point is for the agent to learn its policy.
Which is its strategy, how it decides what action to take given the state.
Exactly. That's what it's trying to figure out, the optimal policy.
Okay, makes sense for the basics. But how does this actually, work in practice when things get complex, like controlling a robot arm or generating human-like text?
Well, the loop is simple conceptually. The agent sees the state, picks an action using its current policy, gets the reward, and the environment moves to a new state.
And then learning happens.
Right. The learning algorithm takes that experience, state, action, reward, new state, and updates the agent's policy. It nudges the policy to make actions that led to good rewards more likely in the future.
So it gradually improves its strategy.
Correct. Some techniques, like Q-learning, focus on learning the expected future reward of taking a certain action in a certain state. Others try to optimize the policy directly.
And when you're dealing with, say, visual input from a camera or massive amounts of text data, that seems too complex for simple value tables.
Absolutely. That's where deep reinforcement learning, DRL, comes in. You use neural networks.
Oh, okay. Deep learning meets RL.
Exactly. Neural networks are great at handling that high-dimensional input, like pixels from an image or sequences of words. They can learn complex policies directly from that raw data.
Which brings us to the LLMs, right? You mentioned RLHF.
Yes, reinforcement learning from human feedback. Super relevant now. It's a key technique used to fine-tune models like ChatGPT.
So how does RLHF actually work? How do humans get involved in the reward part?
It's a multi-stage process. First, you collect data where humans compare different outputs from the LLM. They might rank responses or say which one they prefer.
Okay, so you gather human judgment.
Right. Then you train a separate model, called a reward model, on this preference data. Its job is to predict which output a human would likely prefer. It learns to score outputs based on human taste, essentially.
So the reward model acts like a proxy for the human judges.
Precisely. And then you use an RL algorithm. Proximal policy optimization, or PPO, is a common one because it's pretty stable to fine-tune the actual LLM.
And the LLM's the agent.
Yes, its actions are generating sequences of text. The reward comes from that reward model we just talked about.
So the LLM learns to generate text that scores high, according to the human preference-trained reward model.
You've got it. It's optimizing its text generation policy to align with what the reward model says humans like.
That connection to LLMs is huge. But let's zoom out again. Why does understanding this RL process, the agent, the feedback loop, the policy updates, matter so much to you, the security professional listening?
Well, because this RL paradigm, it's fundamental to a lot of systems you encounter or analyze. Think autonomous systems, self-driving cars, drones, industrial robots. They often use RL.
And those represent pretty complex attack surfaces, right? Dynamic ones?
Definitely. But RL is also used directly in security applications, too. Anomaly detection, automated threat hunting, stuff like that.
So understanding how these RL agents learn and adapt is key.
Absolutely. It helps you predict their behavior. If you know how an agent learns to make sequential decisions based on rewards, you might anticipate how it could fail or where potential vulnerabilities might lie.
Like finding edge cases or unintended consequences of the reward function.
Exactly. An agent is just trying to maximize its reward signal. It might find clever, unexpected, or even undesirable ways to do that from a security standpoint. Understanding that reward function is critical.
And for the LLMs, tuned with RLHF.
Knowing they're optimizing based on a learned reward model is crucial. It informs how you test them. Can you probe their alignment? Find inputs that cause them to generate harmful or biased output because it somehow tricks the reward mechanism they were trained on?
It really gets to the heart of it. Analyzing that training process, the reward shaping, it's essential for understanding the model's defenses and potential weaknesses.
It really is.
Which raises a big challenge, doesn't it? As these systems, driven by RL and sometimes opaque reward signals, get more complex,
Yeah.
how do we actually audit them effectively for these kinds of subtle learned vulnerabilities?
That is the million-dollar question, isn't it? It's a major focus for researchers and practitioners working with these advanced AI systems today. Definitely something to keep thinking about.
That's all for this bite of InfoSec Insight. Until next time, stay sharp, stay curious, and keep breaking things responsibly, of course.